Hello guys, so today welcome to the fourth episode of our Linux troubleshooting series. In this episode, we will be debugging high memory usage in Linux. So, have you ever logged into a production server and seen this, like memory going 98% used? Have you freaked out? And suddenly everyone is panicking, apps are slowing down, SSH feels laggy, APIs are timing out, and dashboards are red. So in this video, I am going to walk you through a different real-world high memory scenarios, simulate them live, and debug them step by step. And by the end of this episode, guys, you'll be able to look at any Linux machine and confidently say, is this normal memory usage, or do we have a leak, a misconfiguration, or a real fire? So let's start with something that confuses most people. Linux will use as much memory as possible, even when nothing is wrong. Why? Because memory sitting idle is wasted memory. So Linux stores frequently accessed files in page cache, buffer writes, cache directories, metadata, all to make things faster. So when someone sees memory used is 80% and freaks out, that's actually normal. What matters is not used, but how much is actually available, whether the system is swapping, whether any processes are actively growing. So once you understand this difference, memory debugging suddenly becomes much easier. So we will see how to check memory the right way. So why free minus h is one of the most misunderstood commands? Because people stare at the used column first, but instead you should look at the available column. Available column tells you what truly is left. This is your true free space. What applications can actually claim. Also look at the buffer cache, the Linux optimization. Look at swap usage. This is a early warning sign. So if a swap is 0 and available memory is reasonable, things are fine. Even 80% used is showing. But if swap starts growing or available memory keeps shrinking, now we may be heading towards trouble. So always make sure to use the free minus h command properly and understand the columns well. Always look at the available column. This gives you the real true space that is available. And also look at the swap usage. If the swap usage is growing, then things are getting out of control and you should start taking memory seriously. Now we will go through each scenario, simulate it, and learn how to investigate it. We will see few scenarios like high cache usage, application memory leak, swap thrashing, and kernel or slab leak. Let's start. So now we will be demoing the normal system using cache using the dd command. But before we jump into the demo, we need to understand one core concept. And this is something that confuses a lot of people when they first look at memory usage in Linux. Linux has a smart file cache. What that means is Linux doesn't like unused RAM. So if your memory is just sitting there doing nothing, Linux thinks, why waste it? So it uses that idle RAM to store data that was recently read from a disk. Things like binaries, configuration files, logs, container layers, database pages, basically anything the system interacts with. Now, why does Linux do this? Right? That might be a question that you might be getting. The purpose is simple, speed. If system needs that same data again, reading it from RAM is way faster than going back to the disk, even if it is a SSD or NVMe. So instead of treating free memory as something to save, Linux treats it as opportunity to optimize performance. And here's the important part. This cache memory is not permanently used. If an application needs RAM, Linux will instantly drop the cache and free that space. So cache is basically a borrowed memory. Keep that in mind. It's a borrowed memory. This is why when someone looks at the command output of free minus h and panics because memory looks nearly full. In most cases, nothing is wrong. The system isn't running out of RAM. It's actually running effectively or efficiently. So let's see how this works in real time. So I'm going to simulate file access and we'll watch how Linux fills memory with cache and then how it releases that cache when another application needs it. So let's jump into the demo and watch Linux caching behavior live. Okay, so let's get started with our demo. So let's start by checking the current memory usage. We will just do a free -h command. So just concentrate on used, free, and buffer cache. So right now buffer cache is small, meaning Linux is not caching much content. So now what next we will do is we will just trigger a file read with td. So here are the commands. You can either create a big file and then read it. So I have given you the command to create the big file, and now I have the big file at my end. So we have a big file. We'll just read it, and we have also kept free-h under watch. So we are also watching it, and we'll see it live how the buffer cache will grow as we read the file. Okay, as you can see, the buffer cache has grown to 1.6 gigs, which was way low before. So Linux stores the file in RAM cache because it predicts that we might access it again, as we saw in the previous diagram. So now it has stored it in the cache and it is expecting that it might be used up again. So now what next we will do is we are checking the memory again. It is all gone up. The used is and the free is 204 MI and the buffer cache is grown. So too many people, especially if they aren't familiar with Linux, this looks like a memory leak, right? But it's not. It's a performance feature. Linux is using free RAM as a disk cache to make future reads faster. So now let's run the dd command again and let's see if it takes the same amount of time or it gets done real quick. So let's fire it along with the time command. You saw it just got done real quick. So this time it finishes much faster and that proves the cache is working. The file was served from RAM instead of being served from the disk. This proves it. And you can see the buffer cache is still at 1.6 gigs. So now it is using it from the RAM, not the disk. Now let's simulate memory pressure. So we will start a memory hungry process. We will use this stress command. If you don't have the stress command, you can do a apt install and install the stress command. So we are simulating an application that suddenly needs a lot of RAM. This is where the magic happens. Just keep an eye on the buffer cache going down. So Linux now has to decide, should it keep the cache or give the memory to a real application that actually needs it. So as you can see, the buffer cache has gone down from 1.6 gigs. It has gone to 718 M. And keep in mind, Linux always prioritizes real applications. So if you take a look here, the buffer cache column has decreased and available memory of application has increased, which was not like this before. So Linux automatically reclaimed cache memory, no crashes, no OOM kills, no intervention from us. This is why RAM showing as used is not wrong. It's a smart usage. So now let's clear cache manually. So you should not do it in production environment because we are manually clearing cache and then we will see how the buffer cache comes down. Here we are manually clearing the cache. It is not advisable to do it in production, but just to learning and demonstration purpose, we are doing that. This will do. Okay. Now, if you see the buffer cache, it has gone down from 1.6 to 72 MI, and the available is 1.6 gigs. So this proves that high memory usage in Linux is often not a problem. It's Linux optimization performance. It is actually optimizing the performance. Cached memory is available memory. It will be released if application needs it. Also, before assuming there is a leak or misbehaving process, always check the buffer cache over here and the value and the swap usage and whether applications are actually starved. So if cache is high, this part, but the swap over here isn't growing, the system is healthy. And if you see this pattern in monitoring tools, especially in Grafana, don't panic. It's not a memory emergency. It's Linux being clever and doing its magic. So in this scenario number two, a real memory leak in an application, we are moving from a normal Linux behavior to something more concerning, a real memory leak. In this demo, we will run a Python script that keeps allocating memory, storing data in a list, and never releasing it. This simulates what happens when an app forgets to free memory, something that happens in real production systems more often than we'd like. So, unlike the earlier cache scenario, this memory is not reusable because the application still owns it. Linux can't reclaim it. So, the Python program on the left side, we'll just start it in the background. So, we'll just do Python 3 and say for leak.py and just ampersand. And then we will, using watch, we will put a watch on the ps command. So one more thing before moving ahead, just a small explanation about this program that we are doing. This is continuously adding 1 MB of data to a list. So because the list is never cleared, the program's memory footprint grows and grows, and it is growing all the time. So this program, what it is doing is it is simulating a common bug where an app forgets to free memory it no longer needs. So we will also add a watch and see what the PS output is. So here our PS is running. So as you can see, the Python process is rising in memory. It is almost 23% and it is growing. So this is a symptom of a memory leak as it is keep on growing. And in the meantime, we'll also see what free is. The output of free minus h is showing up. The used memory is growing and also the available memory is decreasing, as you can see. So these are symptoms of leak. Also, we'll open the htop command. So htop is also showing you the Python is taking up maximum memory. See, it's gone up to 43 point something. So htop is providing us a visualization of memory leak. So how the memory is growing over here, as you can see. So all the symptoms point to a leak, but we need evidence. So the high level tools like PS and htop showed us memory is growing. But to find the source of leak, we need to look inside the process's memory map. So this we can find using a utility called pmap. So this command will break down the process's memory into its fundamental categories. So let's go ahead and do the pmap command. So we'll do pmap -x and 83695 is the process ID and we'll do a tail. So here is where things get interesting. This command will break down memory into categories, that is stack, memory, file backed memory from shared libraries and anonymous memory over here, as you can see here in these columns, right? So anonymous memory is key here. It represents memory allocated dynamically by the application, not tied to a file or storage. And in leakage situation, this is the region that grows. So if we do it again, it might have grown. I think the application got killed with an OM out of memory. We just saw it, right? As it went on, the swap also increased and it did a kill. Now the memory is back at normal, right? So eventually, depending on system limits, the kernel may step in and kill the process with the OM that is out of memory. That is the case what happened right now. So if you want to just wrap it all up, this scenario, normal systems use RAM as cache and that's healthy. But memory leaks show a steady increase in anonymous memory and RSS. So here the RSS was kept on increasing when the Python program was running. And that's a real problem. That gives you a good symptom and good clue that there is a memory leak. Using PMAP, we found out that the anonymous column was also growing up. The memory or script that was allocated. So watching these particular entries grow in size over time is a definitive proof of a memory leak. So let's summarize what we learned in this scenario. The application was designed to continuously allocate memory. We saw it using PS free and htop, how the memory was growing substantially and the available memory was decreasing. Also, the swap came into play. And then we used PMAP to confirm the growth was in anonymous memory, directly allocated by the application. And if kept unchecked, later on, it also did a OM, which terminated the process to save the system from an outage kind of thing. To just prove it, we can just do a dmesg and grep -I and do OM. So if you see, there are OM logs. What these logs are saying. So here it says the system ran out of memory, the kernel allocator attempted to allocate memory and it failed. So the OM killer came into play and it worked. And here, if you see, the guilty process is also identified. Python 3 here. Python 3 is the guilty process here. 83695 was the process ID that we had done a PMAP on. So this gives you a good understanding of the OM that happened. So healthy cache versus memory leak, the first scenario and the second scenario. What's the difference, right? That question might be in your head. So healthy memory usage, that is cache or buffers. Linux uses idle RAM as a smart cache. This memory is reusable. So if an application needs memory, Linux can instantly free this cache. It exists only to speed up disk access, not because an app is consuming memory. So if you go by an analogy that we have on the screen, so cache is like keeping books on your desk because you just use them. If someone else needs the desk, you put them back on the shelf quickly. So temporary books on a desk. So always keep this analogy in mind. So like keeping books on a table, it's temporary. Also key indicators of healthy cache are the buffer cache will always grow. Also available memory remains high and swap usage stays low or zero or untouched. Then if we compare memory leak to this scenario, a memory leak is when a process keeps allocating memory and never releases it, even when it's no longer needed. Memory cannot be reclaimed by the OS. The RSS, that is resident set size, keeps growing. We saw, right, in the demo. It kept on growing. Available memory drops steadily. So the available memory that is there, it keeps on decreasing. Eventually, the kernel then triggers a OOM. We saw that using dmesg in the logs, right? The Python process then got killed through OM. And then in going by this analogy for memory leak, a leak is like someone bringing new books and stacking them permanently on your disk. No matter how much space is needed, the pile keeps on growing. So these books keep on stacking on this table, right? And the symptoms of a real memory leak are the resident set size, that is RSS, keeps increasing over time. This is your main signal. This is where you should understand that it's a memory leak. Also, the available memory that is there, it decreases. Swap usage grows. We saw the swap also started getting used up at the end. And cache does not shrink automatically because real memory pressure exists. And in the end, it gets OM killed. So if you want to compare both of them, in healthy cache, the used memory will stay high. The buffer cache will also stay high. Available memory also stays high. It is a healthy, it's a healthy status here. There is no need to worry. But whereas in a memory leak, the used memory stays high, the buffer cache is low, no cache is being used, and the available memory that is there keeps on decreasing. There itself you should understand it's a leak. Now that we have seen healthy memory usage and a real leak, let's explore one of the most painful memory states on a Linux system, that is swap thrashing. When a physical RAM runs out, Linux pushes memory pages to swap space, which lives on disk. And disk, even SSD or NVMe, are 1,000 times slower than RAM. So when an application constantly pushes pages back and forth between RAM and swap, the system almost freezes. This condition is called swap thrashing. So we will start the demo and we will use the stress tool. So if you don't have the stress tool, you can install it using sudo apt install stress. We will be running the stress with two memory workers with the flag minus minus vm2, and then each will be allocated 700 MB. That will be through the flag minus minus vm bytes 700M, and we'll run it for 30 seconds. You can also increase it. And in our demo, we'll be slightly increasing the VM bytes and also the timeout. So you can see the stress and the output. You can easily will be visible on the vmstat1 output, which we'll be using to observe the swap activity. And before doing the demo, you just need to observe these two columns, that is SI and SO, that is swap in and swap out. So if these numbers increase repeatedly, your system is thrashing. So swap in will be your pages that are read from disk back to RAM, and swap out will be your pages that are pushed from RAM into the disk. So swap space is nothing but a disk, right? So to and fro will be swap in and swap out. Just keep this in mind. Come on. Yeah. So let's go about it. We will do stress with the workers of 2 and 1024M allocated to both the workers and with a timeout of 60 seconds. So it has started. Let's run our vmstat. So as you can see, the swap in and swap out have gradually increasing. They are going up. Also, let's look at the top and see if the IO weight has gone up. The IO weight is also increasing. The swap D that we said that we discussed over here, right? Swap is filling. The swap is also gone over here. It's completely. So this is what swap thrashing was, and if we had a look and if you checked SI and SO, there was clear indication of swap thrashing happening. So these columns are very important to understand. And also the IO weight, a significant increase was observed. So keep a eye on SI and SO and the weight, IO weight. These numbers, as they rapidly increase, it's a indication that you are facing a swap thrashing incident. So in our last scenario, there might be an issue. Like, it's not like not all memory issues come from user applications. Sometimes the Linux kernel itself leaks memory. So this happens when subsystems like networking, file systems, or drivers keep allocating metadata and never release it over time. So the slab allocator grows uncontrollably. So we have a utility called slabtop to diagnose this. So when you suspect this, so when there is a high number of directory entries, file system operations, inode cache, metadata for all files, all these when they are high, you can suspect that it might be a kernel or a slab leak. So kernel level memory leaks are rare, but they are dangerous and they should be kept an eye on. And because they affect the OS itself, the entire OS is affected by that. It's just not one process. So if a slab cache keeps growing and available memory shrinks, but no user process shows rising RSS like how we saw in our previous scenarios, the leak is in the kernel. So in your free time, just take a look at the slabtop command and what output it throws. So I like to present you this field guide to Linux memory pressure. So there are symptoms that you see, and based on those symptoms, you make your decision. So let's start in the middle, the most common cause, the one which we saw first. So if you see high memory pressure usage, but the system feels fine and responsive, the first thing to check is the cache value with free minus m command. The output that you get, if the cache is large, that's actually good news. It means Linux is using unused RAM as smart file system cache. This improves performance because reading from memory is significantly faster than disk. This behavior is healthy and expected, not a memory leak. Now let's move on to the left-hand side, the case of memory leak. That was our second scenario. So if one process keeps consuming more and more memory over time, that's when alarm should ring. We check the resident set size. Using the ps command we did that. And also tools like top and htop help here. So if RSS keeps climbing and never goes down, it's a strong indication of an memory leak, an application memory leak. This is not buffering or caching. The app is slowly not releasing memory back to the system. So it's a clear indication of memory leak. The below one, the right one over here, that was our scenario number 4. So another case of free memory dropping, but no single process looks guilty. In this situation, processes aren't leaking RAM. Instead, memory is being consumed inside the kernel. We inspect this using slabtop command that we saw in the previous scenario number 4. If certain kernel cache structures continue to grow without shrinking, we are likely dealing with a kernel slab leak. So it is more to do with the kernel than the application part. So slabtop is your best friend over here. And the third symptom that we saw is on this right hand side. That is swap thrashing. So if the system becomes extremely slow and disk IO spikes continuously, checking vmstat will usually show high swap in and swap out, the SI and SO columns that we observed, right, with vmstat. This means the system doesn't have enough physical RAM and is constantly swapping pages between the RAM and disk. At this point, the performance collapses. This is what we call swap thrashing. So we covered all 4 scenarios, and using this decision tree, you can make sure and understand what the symptoms are and take your decision based on that. So in summary, high memory usage doesn't always mean there's a problem. Linux memory behavior is nuanced. And by checking the right metric based on symptoms, we can quickly tell whether the system is healthy, leaking, or struggling under pressure. All right, before we wrap up, let's take a quick look at everything we explored today. So first we saw that sometimes high memory usage is actually normal. Linux aggressively uses free RAM as cache to make the system faster. So high usage alone isn't a red flag. So in the first scenario, we used free -h and top commands and also the proc meminfo to identify the cache buffer that was reclaimable. Then we moved into the second scenario, a real memory leak. In this case, RSS, that is resident set size, kept growing because the application never released allocated memory. In this, we learned how to detect this using PSOX, htop, pmap, and finally confirmed it through the OM logs in dmesg. The third scenario showed us something most engineers encounter in production, a swap thrashing. This is when RAM fills up completely and Linux starts pushing pages in and out of swap. Using tools like vmstat, we were able to clearly see swap in and swap out activity. In this, we saw the stress that was there on our systems. Then, finally, we looked at kernel or slab leaks, rare but serious. These happen when memory allocated by OS kernel keeps growing. Even if no user application looks suspicious, tools like slabtop help identify de-entry leaks, inode growth, or runaway kernel objects. This was found in kernel or slab leak. So the big takeaway is high memory usage isn't enough to panic, but patterns matter. The growing RSS that we saw in second scenario, the swap activity, and rising slab allocation are signals that tell you whether a system is healthy or in trouble. Once you spot these patterns, the tools will guide you to the root cause. So once you find out, we saw the patterns in these three, four scenarios, right? Then you can easily use the other tools like PSOX, htop, free -h. All these tools will always help you to take you to the root cause. So final closing line that I like to tell you and I want you to take ahead is, so memory debugging isn't about seeing what is using memory. It's about understanding why, what and why matters here. So if you can tell the difference between cache, leaks, swap pressure, and kernel issues, you're already ahead of time and already ahead of other engineers. So these what and why is very important when you are debugging the memory issues. Stay tuned for the next scenario that we will have in this series. Thank you.